Thank you, Ben, for the introduction. So I'm Sam. I'm an assistant professor in the Department of Marine Geosciences and an IDSC core faculty member. And I am a geologist. I'm not a computer scientist. And in particular, within geology, I study Earth's landscapes. So if you look around, you look out the window here or anywhere else you might go, I want to know, why does the landscape look the way it does and how did it get there? So we can look at one that's pretty close to here, down in the Everglades. It has a look to it. You can quantify it in various ways, topography, what have you. The one up in the upper right in Utah looks very different. So the one out here is the result of landscape architects. But this one, there are some natural processes and differences. So in particular, I want to know, what are the different physical natural processes that shape these landscapes, and how do they differ in different places? What are the various forces that influence those processes, be it climate, other environmental factors, or, of course, humans as well? And given all of that, how have these landscapes changed over time to get to where they are today, and how might they change going forwards into the future? So, of course, I'm not the first person to think about these questions. People have been doing this in earnest for about 150 years in my field. And for much of that history, people have answered these questions in ways that look much like this. You went out in the field, you brought your compass or your hammer or your surveying tools or what have you, and you made a lot of very concrete, in-person, on-the-ground measurements. And we've learned a lot from this. Many foundational papers that still today are highly cited were done like this, and there's still a lot left to learn. There are many scientists today still doing this, myself included. So these techniques are still very important to the science. But at the same time, there are very real limitations to what you can do like this, in terms of the scope and the scale of the questions you can address. So I cannot go out and stand in the river, the middle of every river in the world, or even in the Blue Ridge Mountains. There just isn't enough of me to go around. So if we want to think about answering questions at larger scales, we need to think a little bit more about different ways we can address these questions. So the first efforts to do that in a scale larger than the field observation really got going in earnest in the early 20th century. So once we invented the airplane, it was a pretty straightforward leap to invent the aerial photograph. And in the 1920s and 1930s, the US Geological Survey started to do that across the United States. And so they went around and they took nice pictures of various parts of the world. And then using this device shown here in the middle, called a stereo plotter, you could use two different images from two different angles and map out the topography. And by doing that, they were able to produce topographic maps like this one. Now, it's important to note that these techniques are not replacing traditional field measurements. You can't really see it on this map, but there are a bunch of X's with numbers on them. And each one of those X's is a control point where somebody had to go out on the ground and use traditional surveying techniques to very precisely map the location of that one point. But then by using these more modern techniques, I guess at the time it was big data, you can then fill in the gaps between all of those different control points to create a seamless topographic map. And by doing that, you can quantitatively measure the topography. And it took them a few decades, but they were able to do this over the entire continental United States, which is pretty breathtaking. For the first time in human history, we now had a quantitative measurement of topography over many thousands of square miles. And that's something you could never do with traditional surveying. They would just take too much time. Aren't enough people in the world. So that was kind of the first advance in kind of big data in the earth sciences. After we invented the airplane, the next best thing is the rocket. This here is the first ever photograph taken of Earth from space in 1946. We launched it off of a V-2 rocket that we captured from the Nazis. Now, that picture is not all that useful to a geologist. It's pretty grainy and low resolution. But it still represents the beginning of a new era. And for the next few decades, satellite imagery was primarily the domain of espionage. And so the images were used to spy on the Russians and not released publicly, so they weren't really all that useful to me. There were some weather satellites at much coarser resolution, but in terms of remote sensing, satellite remote sensing for Earth observation, it really got going in earnest in the 1980s. So the US Geological Survey launched the Landsat series of satellite missions, which produced images like this. So this is one of where we are here from the mid-1980s. This is one of the earlier images. And so now we can see kind of the new imagery available. So this has a couple of improvements. So it's now at a resolution that's useful for Earth science applications. So that's a zoom in there of Coral Gables, with the U showing where we are today. And it's not super precise. You can't make out cars in the street, but you can start to make interesting observations of what the Earth looks like from space. The other great thing that this satellite mission had that no one had ever done before is global coverage. So the spy satellites were just looking at a couple missile bases. But this Landsat satellite goes around the entire world, visiting every point every 16 days. So this is a picture of South Florida, but we have these now for the entire world, which we never had before. And of course, since then, it's only gotten better and better. So I'm sure we all today have smartphones in our pockets. You can pull it out, open up Google Maps, and you can see an image like this. That's the building we're in today. It's a little out of date because it's still under construction, but still you can see pretty astonishing resolution. So that picture was taken from space, but you can make out relatively fine features, and we have imagery like that over the entire world. So now it's time to think about what we can do with this new imagery, this new data, that we can address questions at bigger scales than we could before. At the same time as this ever-growing amount of data, we also have new techniques to process it. So we're not just limited to stereo plotters, looking at images from different angles and drawing out contour lines, but we have modern computational techniques that enable us to analyze and process this growing data archive. So I'll share with you briefly a project that I worked on in some of my past research that illustrates how we can do that. So this project was studying Amazonian dark earth, or ADE. So the typical soils of the Amazon, shown here on the right, are bright red in color and very nutrient poor. In contrast, ADE is characterized by its dark color, which is very high in fertility and nutrients, as charcoal and carbon, which is why it's so dark. And it's also full of ceramic fragments indicating a human origin. So these soil deposits were created by ancient inhabitants of the Amazon. So there are a lot of things we would like to know about ADE. Perhaps most simply, how extensive is it? How much of the Amazon basin features these very rich soil deposits instead of the nutrient-poor stuff that's everywhere else? How many archaeological sites are there that contain this? And from that, maybe we can make estimates of how much carbon is stored there. So soil carbon is a major global reservoir of carbon, much bigger than the atmosphere, in fact. So can we try to quantify that? Well, let's think about how we might do that. So in 2010, these people they published a paper where they tried to compile every known location of ADE, of these rich soil deposits. And that's what each one of those blue dots is. That's something that had been reported in the literature. And every one of those blue dots represents something like this, an archaeological site survey. Somebody went out there with a shovel or an auger and basically dug a hole in the ground and saw the soil. And of course, we've learned a lot from this. That's how we know everything we know about ADE. But there are only so many people going around doing this, and the Amazon's really big. So a database like this is inherently incomplete, and probably is actually missing the overwhelming majority of ADE sites. So there are some major sampling artifacts where the sites are mostly places where people have gone to study, places that are easy to access. So all of these gaps in the middle, where we don't see these blue dots, that probably doesn't mean that there isn't ADE there, it just means no one's gone to look for it. So if we want to think about these big-scale questions, how much is out there, we need to move beyond traditional digging a hole in the ground. And as you might guess, the answer lies in remote sensing. So this picture here on the left is a Landsat image. It's in the near-infrared portion of the electromagnetic spectrum. And we can actually see ADE in this image. So we're not directly imaging the soil. This is closed canopy tropical rainforest. What we're actually seeing is a difference in the tree, in the leaves in the top of the trees. So the near-infrared primarily picks up chlorophyll. And so all of these bright patches you can see, these kind of white blobs, those are places with a higher surface reflectance than the near-infrared, which means more chlorophyll and basically more lush vegetation. And that's because the plants growing on this rich soil are doing better than what's on the nutrient-poor soil. So we can see ADE in the satellite image. And of course, we have the satellite imagery anywhere you might want to look over the whole world. So we put together a satellite image over our study area here, put it all together, combined it with some labeled training data. So each one of these bright green polygons here is a known archaeological site where we know there's ADE, there's soil deposit. And the way we know this is, again, through traditional archaeological techniques. So I'm by no means saying we should do away with them. They're still very important. We can't do anything without them. But these remote sensing machine learning techniques can help us take those and then go to bigger scales, starting from that, but then jumping off to questions we couldn't answer before. So when we put it all together in a machine learning classifier, we used a random forest classifier, we can produce a classification map over our entire study area. So that's what this is here. We'll zoom in on the right. And every one of those bright green blobs is a place where we predict there's ADE, this rich soil. There are thousands of these across our study region. This is only a small fraction of the Amazon. Way more than archaeologists have gone out and studied. So this shows us that it's everywhere, and that the blue dots we saw before were just a very small subset of what's actually out there. So now we can start to think about some of those questions at bigger scales that we couldn't before. So we can think about how much area is there. We predict in our relatively small study area about 900 square kilometers of ADE. So that's a substantial fraction, several percent of the total landscape. Then by combining that with soil measurements, we can start to think about carbon, and we can, back of the envelope, speculate that it might contain as much carbon as the annual emissions of an industrialized nation that was put down there into the soil hundreds of years ago by ancient inhabitants of the Amazon, and is still there today. So this ADE deposits were created hundreds of years ago. So to think about those questions, we just use a single snapshot. But we've had these satellites up in space since the 80s, so now we have a 40-year time series. So if you want to think about questions about landscape change, any time scale 40 years or less, we now have a very rich data archive that you can start to dig into. Hopefully this works. It's a YouTube video. I'm not sure if it'll link. Maybe not. Anyway, you just have to take my word for it. It's a very pretty YouTube video. You can see the river meandering across the floodplain over 40 years from Landsat imagery. So moving on, I hope to use that time series, and this is something I'm just starting to dig into now in my research here at the University of Miami, to understand landscape change in the Everglades. So as many of you, most of you probably know, the Everglades just to our west is a wetland ecosystem that's unique to South Florida. And before about 150 years ago, it worked like this. So in the summer, we get a lot of thunderstorms, you all know that. It rains all across peninsular Florida, flows down into Lake Okeechobee, and then it just spills out over the south edge and basically flows across most of South Florida in a very wide, shallow, slow river. But then people came down here, and we decided we wanted to build houses and grow crops, and having a seasonally flooded wetland is not all that conducive to those uses, so we decided we were going to try to change it. So we dug a lot of canals. We also built roads, in particular the Tamiami Trail, running all the way across it, elevated on a raised embankment. This is very disruptive to the natural flow of the water. So now it's something more like this. Most of the water that goes into Lake Okeechobee is diverted out east and west through canals to the ocean, and only a small fraction of what used to go still makes it to what's today left of the Everglades in Everglades National Park. Fortunately, people started to see the error of their past ways and tried to think about how can we restore the landscape a little bit. So the Tamiami Trail there shown on the left when they first built it was originally built as a continuous raised embankment all the way across, basically allowing no water through. But starting in about the year 2000, we started to elevate some portions of this road to allow water to flow back under it. At the same time as these restoration efforts, we also, of course, have climate change going on. So in the last 100 years, we've had about 30 centimeters of sea level rise here, and it's only going to pick up. Because the ocean is the downstream boundary condition of this landscape and it's very low elevation, it's quite sensitive to changes in sea level. We also probably have changes in precipitation or temperature that could be affecting the landscape and the hydrology of the region. So given all of these changes, what I want to know is can we quantify the resulting changes to the landscape using a time series of remote sensing images? So let's think about how much data we have. So the Landsat series of missions goes back to the 1980s, so that's our longest term. But we've also started to put up more and more satellites since then with better spectral resolution, better spatial resolution, and better temporal resolution. So it just keeps getting better and better. The data keep getting richer and richer. So for this one point in the middle of the Everglades with the red star, I just tried to see how many images are out there, and it's about 2,000. So there's terabytes of data. Now some of it's unusable because of clouds. There's about a third of it. But still, that's a lot of data to look at, going back 40 years. So let's think about how we can start to dig into this a little bit. We also have other environmental data we can use. So the US Geological Survey has a series of monitoring stations where they measure the water level. That goes back about 30 years. We have climate records of precipitation and temperature going back several decades. So what I want to do with all of this is kind of bring it all together. So first, from the remote sensing imagery, using labeled training data for different land cover classes, can we classify the full image stack and get the full time series? Using that, can we quantify the landscape change both in terms of seasonal change as the water goes up and down, and long term. Then I want to incorporate these different other environmental variables using physics-based models of hydrology and bring it all together to assess the impact of climate change, of human restoration efforts, and all of the other changes going on the landscape. So we can try to see how is it changing and why is it changing. So that's what I hope to work on over the next few years, and hopefully I'll have more updates to share with you at future IDSC days.
It seemed like they were all close to the rivers and the water, and I was wondering if the crops were doing well there because of the water and not so much the soil.
That's a great question. So it is true. That is the pattern we see, that the ADE deposits and really archaeological sites throughout the Amazon tend to be near rivers. But in terms of the topography, it's basically a continuous bluff, and we see discrete patches of ADE. So there's adjacent forest that's topographically the same, similarly close to the river where we don't see ADE, both in terms of the field observations and also in our remote sensing imagery. So that's probably not the primary driver of variation. It probably has more to do with the ancient inhabitants' preference for easy access to water.
So interesting, thank you. How do you deal with the different resolution in the images across time? Like, I'm guessing that the resolution is getting better and better with time, and so how do you account for that in your analysis? It's
a great question. So the Landsat series of missions is designed to be backwards compatible. So they keep basically adding more and more bits on, but everything that was there in Landsat 5 is still there today. So as long as you make sure you're comparing apples to apples, it's really a very continuous time series, even though they keep putting up more and more satellites. With some of the newer ones coming online, like Sentinel, they are different spectral bands and finer spatial resolution. So the way you need to do that is basically just make sure that, so when you train a classifier, it doesn't really know what you give it to classify, so you need to make sure you're giving it the same thing you trained it on, basically.
All right, thank you, Sam. We'll have to move on.